What if the laws of thermodynamics weren't just math, but a spiritual ledger?
Oh, that is a heavy question to start with.
Right. But I want you, the listener, to just take a second and look around the room you're sitting in right now. Like, look at the lights overhead.
Yeah, or notice the temperature of the air, like whether there's a subtle hum from an AC vent or maybe the dry warmth of a heater.
Exactly. Look at the device you are actually using to listen to this deep dive right now. We are just completely surrounded by these invisible, silent forces that are, tirelessly working to keep our modern lives running.
And if we're being honest, how often do you actually think about them?
I mean, almost never. Usually when we talk about energy, we are just complaining about a utility bill,
Hmm.
right? Or maybe we're skimming some news article about the power grid. It's totally transactional.
It's an inconvenience. It becomes this highly abstracted concept. We basically treat energy as a commodity, just
Yeah.
a line item on a household budget or a talking point in some political debate.
Yeah, totally detached.
Right. We completely detach from the actual physical reality of what energy is, and much more importantly, we detach from our relationship to it. We just expect the lights to turn on when we flip the switch.
With zero regard for the immense, highly choreographed transfer of physical forces that makes that little bulb glow.
Exactly.
And that detachment is exactly what we're going to try to dismantle today. Because today's deep dive is centered on a source that takes everything you thought you knew about basic physics and just it flips the entire paradigm on its head.
It really does.
We've got our hands on this fascinating engineering curriculum. Specifically, it's a slide deck titled Chapter 6, The Energy Blueprint. But I have to warn you, this isn't just a standard, dry university physics lecture.
Not at all. We are exploring this material from a really specific and honestly a profound perspective. It's written by a Muslim lecturer teaching engineering.
Which completely changes the framing of the entire discipline.
It really does, because the goal here isn't just to teach students how to, memorize the strict physics of work, energy, and power. The mission of this curriculum is to deeply integrate those rigid mathematical concepts with Tawhidic principles.
Right, Islamic theology.
Exactly. Specifically, it centers on the concepts of amana, which translates roughly to trust, and khalifa, which means stewardship.
Amana and Khalifa.
Yeah. And these aren't just philosophical footnotes in the syllabus. They are the central load-bearing themes guiding every single equation we are going to look at today.
So we are going to look at equations not just as math problems, but as actual moral frameworks.
That's the goal.
The source material sets this scene immediately with this incredible visual journey. It doesn't start with formulas. It starts by showing us a massive concrete hydroelectric dam holding back a river.
Yeah, and then a sleek electric vehicle with its internal battery cells exposed.
And finally, a sprawling solar farm just soaking up the sun.
And the curriculum calls those things the engines of engineering. It makes it really clear that this is a foundational exploration of physics, systems, and stewardship. Those three images aren't just machines.
What are they then?
They represent humanity's literal interaction with the physical universe. Addressing you, the listener, directly here, this deep dive is tailored to help you see the physical world around you, those lights, your car, your phone battery, as a profound responsibility.
I love that. So let's unpack the core philosophy driving this entire approach, starting with this concept of amana.
Okay, so from a Tawhidic perspective, which is the Islamic concept of the indivisible oneness of God energy, is not merely a resource sitting in the ground waiting to be exploited for maximum profit.
Right. It's not just free real estate.
Exactly. The text explicitly states that energy is a manifestation of perfect creation provided by Allah. Therefore, these resources are an amana. They are a sacred trust. You don't own the energy, you are merely borrowing it.
A trust. Wow. Not a gift to be squandered, but a literal trust to be managed. Which perfectly leads into the role of the listener, and specifically, the role of the engineer.
Because if the energy is a trust, then the person managing it is the trustee. That's the Khalifa, the steward.
And the author actually cites a specific Quranic framework to anchor this. Quoting Surah Al-An'am, verse 165, it says, "And it is he who has made you successors," which is the word Khalifa, "upon the earth, and has raised some of you above others in degrees of rank, that he may try you through what he has given you."
What's fascinating about applying that single verse to this field is how it elevates the discipline of engineering.
Yeah, because engineering usually gets reduced to a purely technical job.
Right. You sit in a cubicle, you run CAD software, you optimize a pipeline, you try to save the company some money. But this framework argues that managing the physical world is a moral and spiritual mandate. The engineer is literally acting as a steward of creation.
And the text actually spells out what that engineer's mandate entails. It's a four-part directive. First, to design systems that meet human needs efficiently.
Second, to minimize waste.
Third, to preserve the environmental balance.
And fourth, by doing all of those things, to honor the creator.
If we connect this to the bigger picture, it's a massive shift in motivation. You are no longer just engineering for a paycheck, or even just for human safety, though obviously that is paramount.
Oh, for sure, safety is a given. But beyond that, you are engineering to fulfill a spiritual responsibility. You are tasked with using energy in ways that are sustainable and beneficial for humanity, preserving the balance and harmony of the natural world.
Wait, I have to ask about how this actually plays out in a classroom. Because normally theology and applied physics are taught in, like, completely different buildings on a university campus. They rarely mix.
Very rarely, yeah.
How does this specific Tohidic framework actually change how an engineering student looks at a math problem on a whiteboard? Like, does it change the math itself?
Well, it doesn't change the math, but it entirely changes the consequence of the math. Think about it this way. In a purely secular capitalist engineering framework, what is a wasted joule of energy? Say a motor runs too hot. What does that actually mean?
It's an inefficiency. It's a slight hit to the profit margin.
Yeah.
Maybe it's a design flaw that needs to be optimized in the next product cycle to save a few cents per unit.
Right, it's a budget problem. It's a line on a spreadsheet.
Exactly.
But under the framework of Amana and Khalifa, a wasted joule of energy is a breach of a divine trust. You have taken something perfect, something entrusted to your care by the Creator, and you have squandered it through negligence or poor design.
Wow.
Yeah. The stakes of getting the equation right are no longer just financial, they are spiritual. The math becomes a ledger of your stewardship.
A ledger of stewardship. That is a heavy responsibility to place on an undergrad trying to pass thermodynamics.
It really is.
But it really makes the math matter so much more. So let's actually bridge this philosophy into the hard physics of work and the scale of potential energy. Because we have to understand what a joule actually is before we can worry about wasting it.
Makes sense. Let's start with the foundational concept of mechanical work.
Okay, let's do it.
In physics, work is the literal bridge between physical effort and motion. And the foundational equation here defines work as applied force multiplied by displacement, factoring in the angle of the force. So W equals the absolute value of F times the absolute value of D times cosine theta.
And the unit of measure is the joule, right?
Yes, the joule. 1 joule is the energy transferred when applying a force of 1 Newton through a distance of 1 meter.
And this is immediately paired in the slides with the work energy theorem, which states that the net work done on an object is equal to its changing kinetic energy.
Right. The core principle is that the net work done on a system is used entirely to change its motion. It's a perfect, unbreakable transaction. You apply force over a distance, and the object speeds up or slows down proportionally.
I always like to use a practical analogy for this because the physics definition of work is so profoundly different from our everyday use of the word.
Oh, totally. People get so confused by this.
Right. So imagine you are standing in front of a solid brick wall and you place your hands flat against it and you push with all your might.
Okay, picture it.
You push for hours. You are sweating. Your muscles are burning. You are completely exhausting your biological energy reserves. You feel like you've done a massive amount of work. But because that brick wall did not move, because displacement is zero physics, says you have done exactly zero work.
It is entirely wasted effort from a mechanical standpoint. Your body converted chemical energy into heat and muscle contraction, but absolutely none of it transferred into the wall as mechanical work.
Exactly. Now compare that to lightly pushing a shopping cart down an aisle. It takes barely any effort, but because the cart is moving, because there is displacement, you are mathematically doing work.
Right.
Now, how does this tie back to the concept of Khalifa we just talked about? True stewardship requires effective action. Just sweating and struggling isn't enough if you aren't actually moving the needle, if you aren't creating displacement. Wasteful, stagnant effort just isn't good stewardship.
That is an excellent connection. The universe demands efficiency to register as work, and so does the mandate of Amana. If you are expending energy without creating useful motion or change, you are failing the equation on both a physical and a spiritual level.
So once we understand work is this bridge, we have to look at the landscape of mechanical energy itself. The deck explains that total energy is the sum of kinetic energy, the energy of motion, and potential energy, the energy of position or state.
Right, and the curriculum breaks this down into 4 distinct forms. This is essentially building a toolkit for the engineer. As a steward of the physical world, you need to be able to identify exactly where energy is hiding and how it is moving.
Let's walk through them. First, you have translational kinetic energy. This is the energy of linear motion. The classic example is a sports car speeding straight down a highway.
And the equation there is 1/2 mass times velocity squared.
And because velocity is squared in this equation, speed acts exponentially, right?
Yes. If you double your speed down the highway, you aren't carrying twice the kinetic energy, you are carrying 4 times the energy. That's exactly why high-speed crashes are so devastating.
Next is rotational kinetic energy. This is the energy of spinning motion. Instead of linear speed, we're looking at how fast something is spinning and how its mass is distributed around the center of rotation.
The math here is 1/2 I times omega squared. Think of a massive flywheel or a set of complex interlocking gears inside a turbine. Its energy stored in the act of turning.
Then we move to potential energy, starting with gravitational potential energy. This is energy stored by virtue of height or position relative to gravity.
Right, mass times gravity times height. MGH. Think of a heavy steel beam suspended by a crane high above a construction site. It's latent power just waiting for gravity to pull it down.
And finally, elastic potential energy. This is energy stored by the physical deformation of a material like compression or stretching.
The key factor here is the spring constant, or stiffness, of the material, multiplied by the distance it's compressed or stretched, squared, so 1/2 kx squared. A heavy-duty industrial spring coiled under pressure is just packed with elastic potential energy.
And to really demonstrate the sheer awe-inspiring scale of what we are dealing with when we talk about energy, the source material does a deep dive into hydroelectric potential. We are looking at a case study comparing 2 real-world dams in Malaysia, the Bakun Dam and the Kinyer Dam.
And the numbers here are absolutely staggering.
They really are. Let's look at the Bakun Dam first. It is an absolute behemoth of engineering. It stands 205 meters high. Its reservoir capacity is roughly 43,800 million cubic meters of water.
Okay, that is a lot of water.
Right. Now, using that gravitational potential energy concept, mass times gravity times height, the lecturer calculates the estimated potential energy stored behind that wall of concrete.
And the number is almost impossible to comprehend. It yields approximately 8.8 times 10 to the 15th power joules. 8.8 petajoules.
Petajoules. I don't get it.
Let's contextualize what a petajoule actually is, because the human brain struggles with numbers that large. 1 petajoule is equivalent to the energy released by burning tens of millions of gallons of gasoline.
Oh my gosh.
It is an apocalyptic amount of force. We are talking about millions of billions of joules just sitting there completely still, stored purely in the immense height and mass of that water pressing against the concrete.
Now compare that to the Kinyer Dam. Still a massive structure, but smaller. It's 155 meters high, holding about 13,600 million cubic meters of water. Its estimated potential energy is about 2.1 petajoules.
And the specific insight the lecturer highlights here is the exponential scaling effect of gravity and mass. Like, the Bakun Dam is only 50 meters taller than the Kinyer Dam.
205 meters versus 155 meters.
That's a significant height difference, sure, but look at the energy difference. It jumps from 2.1 petajoules to 8.8 petajoules. It more than quadruples.
Because you aren't just adding a little bit of height, right? That extra 50 meters of vertical height allows you to push the water back up the valley, exponentially increasing the volume and therefore the mass. That 43,800 million cubic meters of water.
Exactly. The mass and the height multiply together to create this massive reservoir of latent power. This is engineering on a planetary scale. You are literally reshaping the geography of the Earth, flooding entire valleys to build a colossal battery out of gravity and water.
And returning to the overarching theme, wielding that kind of power requires immense mana. If a dam of that scale fails, it's not just a mechanical failure. It's a catastrophic destruction of life and environment.
Truly. And even if it doesn't fail, if it's built inefficiently, it's a massive waste of ecological resources. Flooding that much land destroys habitats. The engineering must be as perfect as humanly possible because the scale of the trust is so vast.
But the curriculum doesn't just focus on the massive planetary scale engineering. It pivots to the everyday microscopic management of energy. It transitions from millions of tons of water behind a dam to the suspension system of a car bouncing down a potholed road.
Right, we're moving to that fourth form of energy, elastic potential energy. And the core discussion here contrasts two distinct ways engineers manage the kinetic energy of a bumpy road. It looks at coil springs versus leaf springs.
We've all seen coil springs. They look like giant slinkies made of thick steel wire, helically wound. Their function is to absorb the kinetic shock of a pothole by rapidly compressing and expanding.
Yeah, the metal twists slightly as it compresses. They are highly flexible, highly responsive, and ideal for vehicle stability and passenger comfort. They are what make your daily commute in a sedan feel smooth.
But they have a constraint. They're less suitable for incredibly heavy industrial loads. That's where leaf springs come in.
Right. If you look under the rear axle of a heavy-duty pickup truck or a commercial semi-truck, you won't see coils. You'll see these layered, curved metal strips stacked on top of each other.
They look almost like a bow from a bow and arrow, just bolted directly to the axle.
Exactly. They still absorb shocks, but the mechanics are different. As the axle hits a bump, those curved metal leaves are forced to flatten out, sliding slightly against each other. They are significantly stiffer, meaning their spring constant is much higher, and they are much less flexible than a coil spring.
So they are engineered explicitly for hauling heavy loads, keeping the axle perfectly located even under tons of stress.
Yep. And the beauty here is that by understanding the physics, engineers can completely control the chaos of a bumpy road. By altering the stiffness of the material, by choosing a flexible coil for a luxury car or a stiff stack of steel leaves for a dump truck, they dictate exactly how that violent kinetic impact from a pothole is absorbed and stored.
They tame the physical world to serve a specific human need.
Which brings us perfectly to the next major concept in the slides, the chaos of heat and the mandate of balance. We've talked about the macroscopic, visible world dams, cars, springs. Now we are forced to look at the microscopic realm. We are diving into thermal energy.
I love how the text frames this. Thermal energy is driven entirely by the random motion of particles. When we zoom in far enough, nothing is actually still. The desk you are sitting at, the air you are breathing, it's all just atoms vibrating, bouncing, and colliding furiously.
And that random chaotic motion is exactly what we experience as temperature. The equation here is Q equals mc delta T. The faster the atoms vibrate, the hotter the object feels. And there's a really important historical note here in the curriculum.
Oh, about calories.
Yeah. The text explicitly links thermal energy to mechanical work, noting that both are measured in joules, replacing the historical use of calories.
This was a massive paradigm shift in physics, right?
Yeah.
Because for a long time, scientists thought heat was invisible fluid called caloric that flowed from hot things to cold things like water flowing down a hill.
Precisely. It sounds silly to us now, but that was the prevailing theory. But experiments in the 19th century, notably by James Prescott Joule, proved that mechanical work like violently stirring an insulated vat of water with paddles could actually generate heat.
The friction of the paddles physically sped up the water molecule.
Exactly. Heat and mechanical work are the exact same currency. They're just different manifestations of energy. That's why they share the same unit, the joule.
Okay, so adding thermal energy increases temperature by making the atoms vibrate faster. But what happens when things freeze or boil? I remember this from high school chemistry, and the math always felt completely counterintuitive.
It does get weird. We are talking about phase changes, which the text defines beautifully as breaking bonds. When matter changes state, say, from solid ice to liquid water or liquid water to steam, the equations shift. We look at the latent heat of fusion or vaporization.
And the critical concept is that during a phase change, heat breaks atomic bonds without changing the temperature. Like if you have a pot of boiling water on the stove and you crank the gas burner up to maximum, the water does not get any hotter than 100 degrees Celsius. It just boils faster.
Right, because all that extra thermal energy you are pumping into the system from the flame isn't increasing the random motion of the liquid water molecules anymore, which is what would increase the temperature. Instead, that energy is entirely consumed by the literal breaking of atomic bonds, violently ripping the liquid molecules apart to turn them into a gas, into steam.
It's wild. The energy goes into changing the state of the matter, not its temperature. It's like a hidden vault of energy.
And understanding this hidden thermal dynamics isn't just academic. It has massive real-world applications. The text uses a fascinating example, the HVAC challenge, or building climate control.
Managing thermal energy in a building is honestly one of the most complex balancing acts in modern engineering.
Yeah.
The stakes are laid out clearly in the slide. Heating systems have to counter winter heat loss, AC systems have to counter summer heat gain, and ventilation has to manage humidity and indoor pollutants.
You are constantly fighting the external environment to maintain a tiny bubble of artificial equilibrium for human comfort.
And to do this, the lecturer contrasts two completely different systems to show how engineering choices impact our stewardship. First, you have the ACSU, the Air Conditioning Supply Unit, often called a single-split system.
Imagine a large, centralized unit sitting on the roof of a building, blindly blowing cold air through a massive, complex network of metal ductwork hidden in the ceilings.
Yeah, we've all seen those vents.
It's highly centralized. The installation is complex because running giant metal ducts through a building takes up a lot of physical space. It's generally best suited for large, wide-open zones like a gymnasium or a factory floor.
But the trade-off is that it typically has a lower initial installation cost.
Right.
Yes, but the operating costs are terrible because it's a blunt instrument. You are often cooling the entire volume of air in a building whether people are in every corner of the room or not.
Now contrast that with the VRV system, the Variable Refrigerant Volume System.
Yeah.
The architecture here is totally different. No massive central air ducts.
None at all. Instead, you have one outdoor unit connected via small, easily routed refrigerant pipes to individual decentralized cooling units in every single room.
So the control is totally decentralized.
Exactly. The installation is much more flexible because snaking small copper pipes through a wall is far easier than installing giant metal air ducts. It is ideal for mixed or multi-zone spaces like an office building with dozens of separate enclosed rooms.
And the cost profile flips. It's a much higher initial cost to buy all those individual smart units and the complex sensors to run them, but the operating costs are incredibly low because you only cool the exact rooms that are occupied. System senses where the heat is and targets it surgically.
And this is where the lecture explicitly connects thermodynamics back to the Taoidic concept of amana. Controlling a building's climate is one of humanity's absolute most energy-intensive tasks. It consumes a massive percentage of the global power grid. Every day, we burn mountains of coal and natural gas just to keep our offices at 72 degrees.
So true stewardship acting as a responsible Khalifa means you can't just pick the cheapest system up front to save the construction budget. You have to analyze the use case.
Right.
If you install a centralized ACSU in a highly segmented office building, you'll spend decades dumping mechanically cooled air into empty conference rooms.
Yeah.
You are failing the mandate to minimize waste.
Choosing the advanced VRV system, despite the upfront cost, is a direct application of moral stewardship to avoid the sin of wastefulness. The engineering choice is quite literally a moral choice.
Which brings us to the next logical step. If our moral mandate as a Khalifa is to stop wasting energy in our buildings, it inevitably forces us to look at where we are getting that power in the first place. Are we sourcing it responsibly?
That leads directly into the discussion on sustainability and the economics of stewardship.
Because the demand for sustainable engineering is no longer a fringe environmental movement, it is an absolute requirement for the future of the species. The curriculum maps out the transition to replenishable energy, listing sources like ocean tidal power, biomass, geothermal heat from the Earth's core, hydroelectric dams, wind, and solar.
And the advantages of these sources are exactly what we desperately need. Reduced greenhouse gas emissions, long-term energy security. Nobody can put an embargo on the sun or the wind.
Very true.
Environmental protection, and massive economic growth in these new technological sectors.
But I want to pause here because we hear this all the time. If the math on solar and wind is this good and the environmental benefits are this obvious, why are we still burning coal? What is the actual engineering bottleneck preventing us from going 100% renewable tomorrow?
The engineering reality is brutally complex. You can't just flip a switch. The text highlights three massive constraints. First, and most importantly, is intermittency.
All right, the sun sets every night. The wind stops blowing unpredictably.
Exactly. To run a modern 247 civilization on solar and wind, you require massive grid-scale energy storage solutions batteries on a scale we haven't fully perfected or deployed yet.
The energy isn't always there exactly when the demand spikes, like when everyone gets home from work and turns on their AC at the same time.
Precisely. The second major bottleneck is grid integration. Our current national power grids were built a century ago for a one-way flow of power. From a massive centralized coal or nuclear plant out across transmission lines to the consumer.
Yeah.
Feeding highly fluctuating, decentralized power from millions of rooftop solar panels back into these aging, rigid grids requires incredibly complex smart grid technology to prevent overloads and blackouts.
And the third challenge is always the bottom line, initial costs. Building a massive offshore wind farm requires colossal upfront capital for the infrastructure, the specialized ships, the underwater cabling, all before a single watt of power is generated.
So the question becomes, how do we bridge that gap? How do we incentivize this massive societal transition when the upfront hurdles are so steep? That's where policy has to meet technology.
And the curriculum explores this using a fascinating real-world example from Malaysia, the feed-in tariff, or FIT system.
Yes.
This is one of my favorite parts of the curriculum because it takes these grand global ideas and makes them incredibly tangible. They actually look at a literal domestic electric bill from Malaysia, dated August 2024. Let's walk through this because it's brilliant.
Go for it.
On the bill, amidst all the standard charges for kilowatt hours of electricity used by the homeowner, there is a specific line item, the KWTBB surcharge, which is set at 1.6%.
KWTBB stands for the Renewable Energy Fund. What this means is that every single domestic user pays a tiny 1.6% fraction extra on their monthly bill. That money doesn't just go to the utility company's profits. It is collected and pulled together into a national fund to directly finance Malaysia's feed-in tariff system.
And the FIT system is the mechanism that makes solar panels affordable for the average citizen. If you install a hybrid solar system panels on your roof, an inverter, maybe a battery, you aren't just powering your own television. During the day when the sun is shining and you generate more power than your house needs, you feed that excess renewable energy back into the national grid.
And because of the FIT policy, the government pays you for that energy, often at a premium rate. But where does the government get the money to pay you that premium?
From the fund.
Exactly, from that 1.6% KWTBB surcharge that everyone else is paying on their bills. It creates this profound financial loop.
It's incredible. It is the exact concept of Khalifa institutionalized into public policy. Think about the psychology of that. Every single citizen, even if they live in an apartment building and physically cannot install solar panels, is making a micro contribution to a macro-level environmental transition.
Yep. They are collectively funding the stewards who are actively harvesting solar energy.
It transforms a mundane monthly utility bill into a mechanism of collective societal stewardship. It proves that energy policy isn't just economics. It's a reflection of a society's moral values.
But as much as we strive for perfect stewardship, we have to face the darkest reality of engineering. We can never keep all the energy we capture. This brings us to the physics of conservation, inevitable loss, and destructive transformations.
This is where the physics gets a little depressing. The text states the universal law, the first law of thermodynamics. In an isolated system, total energy remains constant. Energy cannot be created or destroyed. It can only change forms.
It's an absolute law of the universe. If you have a closed loop, say, chemical energy in a gasoline engine turning into mechanical kinetic energy, which turns into electrical energy in an alternator, which turns into thermal heat, the total amount of joules in that entire system never changes.
But then, the text drops the hammer with the reality of engineering. While total energy is strictly conserved by the universe, useful energy is constantly, relentlessly lost. The universe taxes every single transaction you make.
And that tax is primarily paid in friction and heat. You want an electric motor to spin to drive a conveyor belt, but the metal bearings inside the motor create physical friction, which generates heat.
Right.
That heat is energy bleeding out of your useful mechanical system into the surrounding air. The energy wasn't destroyed, but it's lost to you forever. You can't use it to turn the belt.
To make this visceral, the curriculum dives into the physics of a car crash. This is a horrifying but perfect example of destructive transformation. The setup is simple. A heavy car, moving at high speed, carrying a massive amount of initial kinetic energy, collides head-on with a stationary concrete wall and stops completely.
The key takeaway here is that mechanical energy is not conserved. The car was moving fast, now it is totally still, the kinetic energy is gone. But because of the first law of thermodynamics, the total energy must be conserved. So where did all that violent kinetic energy go in a fraction of a second?
The text breaks it down into three primary destructive destinations. Let's go frame by frame. First and primarily, thermal energy. As the steel and aluminum frame of the car violently deforms and crushes inwards, the extreme friction of the metal atoms grinding past each other causes the kinetic energy to spike into heat.
The crushed metal of a wrecked car is actually physically hot to the touch immediately after impact.
Wow, I never thought about that. Second, potential energy. Modern cars have engineered crumple zones. These are sections of the frame designed to fold and deform in specific patterns. They act like highly stiff, unyielding springs. They absorb massive amounts of energy by permanently changing the physical shape of the material.
And third, sound energy. That deafening, horrific bang of a car crash, that is an acoustic shockwave. It is literal kinetic energy transferring into the air, vibrating the air molecules forcefully enough to rattle windows and damage your eardrums.
So the kinetic energy of the speeding car didn't vanish. It just scattered chaotically into intense heat, permanently warped metal, and a violent sound wave.
But engineers don't just study these chaotic transformations to understand accidents. They harness them intentionally. They take that destructive physics and use it to save lives. Think about automotive brakes. It's essentially the art of taming kinetic energy.
Right. When you are driving down the highway at 70 miles per hour and a deer jumps into the road, you have to somehow bleed off all the kinetic energy of a 2-ton vehicle safely and immediately. How do you do it?
The mechanism of automotive brakes is actively converting the vehicle's kinetic energy into extreme thermal loads via friction. You are intentionally creating a localized, controlled version of that car crash deformation, but isolating it to the wheels.
You press the brake pedal, hydraulic fluid amplifies your foot's force, and the brake pads clamp down violently on a spinning metal disc attached to the wheel. The intense friction between those abrasive pads and the steel disc violently rips the kinetic energy out of the moving car and turns it directly into blistering heat.
But there is a massive, terrifying danger here, which is called brake fade.
Yeah, brake fade is scary.
If that heat is not removed from the braking system incredibly quickly, the entire assembly overheats. We are talking hundreds of degrees. When that happens, the chemical resin in the friction material on the brake pads can actually boil and glaze over, becoming smooth as glass.
That's bad.
Or the hydraulic brake fluid itself can boil, introducing compressible gas bubbles into the brake lines. When either of those things happen, the system fails. You press the pedal to the floor, but the car doesn't stop.
So how do engineers solve this massive heat problem? The curriculum explains why modern cars use ventilated disc brakes instead of the older drum brakes.
Drum brakes enclosed the friction components inside a solid metal cylinder. They were robust, but they trapped the heat inside. The solution for high performance or heavy vehicles was the disc brake, specifically ventilated discs.
If you look closely at the brake rotor on a modern car wheel, it isn't a solid piece of steel. It has cooling fins and hollow airflow channels sandwiched between the two friction surfaces.
Right. Those internal vents are explicitly engineered to act as a centrifugal fan. As the wheel spins, it actively pumps cool ambient air from the center of the wheel outward through the hollow disc. It sheds that massive thermal load rapidly through all three methods of heat transfer.
Conduction through the metal, convection as the air pulls heat away, and radiating heat outward. They're taking the deadly kinetic energy of a speeding vehicle and dissipating it safely into the atmosphere as heat.
Which brings us to the ultimate metric of all engineering: efficiency. The text defines efficiency simply as the exact ratio of useful output to total input. And it uses a highly sobering diagram of an internal combustion engine, an ICE, to illustrate this.
This diagram is rough for any car enthusiast to look at. You put 100% chemical energy in. That's the highly refined gasoline and oxygen entering the combustion chamber. But what actually comes out? You get some useful output, the kinetic energy that turns the crankshaft and moves the wheels.
But the massive arrows pointing away from the engine represent wasted heat energy from the exhaust pipe and engine friction, and chemical exhaust, primarily carbon dioxide and water.
The constraint stated in the text is absolute.
Mm-hmm.
In real-world engines, energy output is always less than energy input due to friction, heat, and material resistance.
Mm-hmm.
An internal combustion engine is terribly inefficient. Often only 20 to 30% of the energy in the gasoline actually makes it to the wheels to move the car forward.
Think about that. You pay for a gallon of gas, and 70 to 80% of what you just paid for does absolutely nothing but make the engine block hot, vibrate the chassis, and blow hot gas out the tailpipe.
And here is the profound theological implication of this section, tying back to the concept of amana. Human engineering, bound by the strict laws of physics, is inherently imperfect. We can never achieve 100% efficiency. Every single machine we build bleeds energy.
From a Talmudic perspective, only the Creator is 100% efficient. Human endeavors are defined entirely by how we manage our inherent imperfections and minimize our unavoidable waste. Our stewardship is judged not by achieving perfection, which is physically impossible, but by our relentless pursuit of optimization.
And that relentless pursuit of optimization is exactly what the final sections of the text focus on, the relentless march of power and new paradigms. Because engineers aren't just accepting the 20% efficiency of a gas engine, they're fundamentally rewriting the baseline. And the clearest example of this paradigm shift is electric vehicles.
We just talked about how terrible the internal combustion engine is at efficiency. The curriculum contrasts that with EVs, and it's practically a different universe. EVs routinely operate at 85 to 90% efficiency.
Let's break down why that gap is so massive. Why is an EV so much better at honoring the amount of energy? First is the energy conversion itself. In gas car, you're relying on thousands of contained violent explosions every minute.
You burn fuel to create rapidly expanding hot gases, which shove a metal piston down, which forces a crankshaft to turn. It is a violent, multi-step mechanical nightmare that loses massive amounts of energy to heat and friction at every single step.
Contrast that with an electric motor. It converts electrical current directly into rotational magnetic fields, which seamlessly spin the axle. There are no explosions, no reciprocating pistons scraping against cylinder walls.
Yeah.
It's an incredibly direct, elegant, and frictionless transfer of energy.
Second is idle energy use. When you stop at a red light in a gas car, the engine has to keep spinning, burning fuel just to keep itself alive so it doesn't stall when the light turns green. It's literally burning energy to go 0 miles per hour.
An EV. The motor simply stops drawing power from the battery. Zero waste.
Third, and perhaps most ingeniously, is regenerative braking. We just discussed how standard disc brakes waste kinetic energy by violently turning it into useless heat to stop the car. In an EV, when you lift your foot off the accelerator, the electric motor physically runs in reverse.
It becomes a generator.
Yes. It takes the kinetic energy of the moving car, uses it to spin magnets past coils of wire, and converts that kinetic energy back into electricity, sending it straight back into the battery. It actively recovers the energy that gas cars literally burn into the atmosphere.
And finally, transmission losses. A gas car requires complex drivetrains, clutches, multi-speed gearboxes, and heavy fluid torque converters just to keep the engine in its narrow power band. Every moving gear tooth steals a tiny bit of efficiency.
EVs have incredibly simple drivetrains, often just a single-speed reduction gear. Fewer moving parts means less friction, which means less waste. EVs are a perfect example of engineers fundamentally rewriting the baseline of what is acceptable waste.
But it's not just about efficiency, it's also about rate. It's about how fast you can move that energy.
Yep.
And that brings us to the definition of power.
Power is one of those words we use colloquially all the time, but physics has a very strict definition. Power equals work divided by time, or energy transferred divided by time. The unit is the watt, which is exactly 1 joule per second.
The distinction here is crucial. Power is not just the capacity to do work, it is the relentless speed at which that work is executed. Think of it like this. You and I can both lift a heavy box of books up a flight of stairs. We both do the exact same amount of work, measuring the joules required to overcome gravity.
But if you run up the stairs in 5 seconds and it takes me 50 seconds, you have generated 10 times the power. Power dictates true performance capability.
Now, understanding power and time allows us to track energy over periods of use, which exposes some very uncomfortable truths about our modern lifestyle. The text uses an incredibly relatable, everyday example, the RGB wireless charger.
This scenario is brilliant because it forces us to look at our own daily habits. You have a flashy, glowing wireless charging pad on your desk. It supplies 10 watts of power. Your phone battery stores energy at roughly 70% efficiency via wireless magnetic induction.
The question posed is, how much energy is actually stored in your phone after 2 hours of charging?
The math is straightforward, but the implications are revealing. First, we calculate the total supplied energy. Energy equals power times time. The power is 10 watts. The time is 2 hours, which we must convert to seconds. 7,200 seconds.
So 10 watts multiplied by 7,200 seconds gives us 72,000 joules. That is the total amount of energy the charger pulled from the wall outlet and the power grid.
Now, we apply the system efficiency. The phone only captures 70% of that energy across the wireless gap. So 0.70 times 72,000 joules equals 50,400 joules actually captured and stored by the battery.
Let's do the subtraction there. 72,000 joules pulled from the wall minus the 50,400 joules stored leaves a deficit of 21,600 joules. Where did they go?
They were lost purely to heat. Your phone gets warm, the charging pad gets warm. That energy is wasted.
And this is where the lecture forces the students to analyze the hidden cost of convenience. Why do we accept losing 30% of our energy? Simply so we don't have to spend 2 seconds plugging in a USB cable.
Is sacrificing 21,600 joules of energy, which we just defined as a sacred trust, and a mana worth a tiny incremental increase in desktop convenience?
It is a micro-failure of stewardship that we perform every single day without a second thought.
It's those little leaks that sink the ship. But the curriculum doesn't leave us wallowing in small-scale domestic waste. It immediately scales back up to the absolute pinnacle of human architectural ambition to show what managed, intentional power can achieve when properly harnessed.
It asks us to calculate the power required to build the Merdeka 118 tower.
This is a breathtaking feat of engineering. The Merdeka 118 in Kuala Lumpur is a mega-tall skyscraper, one of the tallest buildings in the entire world. The focus here is on the self-climbing tower cranes used to build it.
These cranes operate over 78 meters tall, weigh 200 tons themselves, and literally climb the structure as they build it upward into the sky.
The physical problem posed is this. Calculate the mechanical power required for this tower crane to lift a 5-ton load of steel, that's 5,000 kilograms, roughly the weight of 2 large SUVs, at a constant vertical speed of 2 meters per second against the pull of gravity.
We walk through the calculation. First, we find the force required to counteract gravity. Force equals mass times gravity. So 5,000 kilograms multiplied by 9.8 meters per second squared gives us 49,000 newtons of downward force.
To lift the load, the electric winch motors on the crane must pull up with at least 49,000 newtons. And we know the upward velocity is a brisk 2 meters per second. So we use the power in motion equation. Power equals force times velocity.
49,000 newtons multiplied by 2 meters per second equals 98,000 watts, or 98 kilowatts of power.
98,000 watts, just to lift one single load of steel beams. The sheer scale of power required to manifest human architectural ambition is staggering. It requires mastering the equations, mastering the heavy machinery, and channeling immense, dangerous forces safely over years of construction.
It is the ultimate expression of the Khalifa managing the physical world.
Which leads us perfectly into the grand synthesis of this entire curriculum. It presents a complete architecture of engineered energy systems. It's a flowchart that summarizes the entire journey we've been on.
It starts with sourcing, harvesting latent energy from gravity, like our massive hydroelectric dams, or from nature, like solar and wind.
That sourced energy is then subjected to transformation. Mechanical work applies force to move the system. Kinetic and thermal changes occur under the absolute, unbreakable law of conservation total energy. In always equals total energy out.
But within that messy transformation, the energy splits into two paths. The useful output, like the mechanical motion of an EV, and the unavoidable loss, usually thermal friction heating up the atmosphere.
And finally, it arrives at optimization. This is where the engineer lives. Engineers measure their success by maximizing that useful ratio, that's efficiency, and managing the precise rate of transfer, that's power, measured in watts.
Sourcing, transformation, optimization, it's the entire physical universe boxed up into 3 steps.
But the lecture doesn't end with a flowchart. They provide a final reflection, bringing us full circle to the very beginning. The core message is this. By understanding how energy behaves, its forms, its conservation, its rate of transfer, engineers gain the specific tools necessary to analyze, design, and optimize the modern world.
But then comes the synthesis under the heading Beyond the Math. The text reads, "Equations are not just rules of physics, they are the parameters of our stewardship. This knowledge allows us to develop solutions that meet human needs efficiently, minimize environmental waste, and preserve the ultimate balance of creation."
And then the lecturer lays down the final standard, the ultimate thesis statement of this entire deep dive. To engineer efficiently is to respect the trust we have been given.
It perfectly fuses the rigid, unforgiving decimal point mathematics of joules and watts with the profound spiritual responsibility of a mana. The technical skills of an engineer aren't just for building faster cars or taller skyscrapers to make money. They're the precise tools required to honor the creator by preserving his creation.
What an incredible journey this has been. We started with the metaphysical concepts of amana, divine trust, and khalifa, moral stewardship.
We grounded those lofty concepts in the rigid math of mechanical work and thermodynamics. We look at the staggering planetary scale of hydroelectric dams, the chaotic, violent physics of car crashes, the terrifying reality of brake fade, the revolutionary efficiency of electric motors, and the massive power required to build megatall skyscrapers.
And we viewed all of it through the unified, purpose-driven lens of a Muslim engineering lecturer trying to instill a sense of profound responsibility in their students.
I'm addressing you, the listener, right now.
Mm-hmm.
After unpacking all of this, you will likely never look at your electric bill, your car brakes, or even your simple wireless phone charger the exact same way again.
The physical world is no longer just a passive backdrop to our lives. It's an active ledger of our interactions and our responsibilities. Every transaction of energy, from the massive dam to the tiny wireless charger, is visible to us now.
Exactly. So I want to leave you with one lingering question to chew on, something that builds on everything we've explored today. If every single joule of energy we interact with is a divine trust, an amana, how does our daily passive consumption of power, leaving a light on in an empty room, letting a gas car idle in a driveway, or intentionally opting to lose 30% of our power to heat just for the convenience of not plugging in a phone, how does that reflect on our ultimate spiritual ledger?
Are we truly acting as the responsible Khalifa of our modern world, or have we let the invisible forces become a little too invisible?